open your calculus algebra. Let's see what's there in algebra. And do you guys have the statistics of the people who asked the weird question? I know. We have an idea.
The statistics of what?
I can't hear what you're saying.
Oh no, you asked, do we have the statistics? And I'm asking of what?
Of the people who moved this test. I don't know. Proper term. The test one was last. Do you have an idea
Of how many people passed? Is that what you're asking? Sorry, it cut out there.
Yep, that's what I'm asking.
No, I don't have a statistic, but when I was looking through the papers when I went to go get mine, I've never seen so many zeros in my life.
Because I think there was someone who was like, guys, you should go and get your papers now because our zeros are floating there. I'm like, what's going on?
There were so many zeros. Yo.
Yeah, I think when I went to go collect my papers in the algebra pack, I only saw one pass.
Is it?
Yeah, I think I saw, no, I lie. I saw a 17 and a 21.
And yeah, maybe the question I should ask is what's going on there? What is going on?
I know, like, for me personally, it wasn't that I won't say I knew the work, but it was a matter of method on how I calculated. So with the stuff that I did know, I didn't get all the marks because I would skip steps. So I lost on that, and then the things that I didn't understand, I wouldn't get marks there. So that cost me.
For
me,
yeah.
I spent all of my time, like, we only had, I think, an hour and a half, so 30 minutes each paper. So I ended up spending like 45 minutes on the first paper, and that was the only one I passed. And then I had too little time for the other two papers, and I would rush them, and then obviously I did badly. But it was a time for me.
Oh yeah. So sounds like the experience was not nice at all. Because I was shocked. And just as a side comment before we begin, so some of you were saying something is wrong with the maths guides, with lecturers, and you guys should strike because last year you got distinctions, and what is wrong? And I think an answer to that question partly is I think it was your first time having a sit-down exam, isn't it?
Yeah, the last time we wrote a maths test was in matric, well, personally for me.
Exactly. And then someone is like, hey, I never thought I'd get a 6 in maths because obviously there were many people who were getting 1-digit marks. So I hope at least you guys have covered. I hope so. I hope you did. Okay, cool. So let's see what's going on. Where is question 1 of algebra? So before we start with question 1, I'm just gonna make a few comments. And okay, I hope you can see my screen. Question 1. So for question 1, they were saying find the principal value, the argument for the complex number, and you were given that complex number. So to some extent, I think all of you can do this problem, but the issue was many of you are struggling with complex numbers fundamentally. So I'm just going to make a quick comment. Okay, so a standard complex number looks like this. And immediately when we deal with a complex number, when we introduce powers to this complex number, it should ring automatically in our heads that we should actually use the Euler form, or others they call it the argument modulus form. Because you cannot raise a complex number to a huge power like 10 and expect to multiply 10 brackets and then expand and solve for the angle. It's a lot of work. So if we have a complex number, as an example, a plus ib to the power of n, trying to make n brackets, which I assume someone somewhere did, is definitely not gonna work till you reach the n bracket. So all what you guys were supposed to do here was first take the complex number, which is in bracket, write it as re to the I theta, right? And remember that r, we are referring to this complex number. R is simply the square root of a squared plus b squared. Nice and easy. So in our case, our r was, our a, if you look carefully, it's -1. Our b, if you look again, it's gonna be a 1. And the answer there is gonna be square root 2. So that's done, it was easy. I think the part which is not hard, but interesting, is figuring out what is your beta. So if you have attended sessions we've done before, so I always say for your theta, make sure you are using the principal argument. So you'll see how it makes our life to be simple. So a quick sketch of the real imaginary axis. The side we have the real axis, and going up and down we have the imaginary axis. So if a complex number, that complex number is z, is a plus ib. If you look at the complex number and you realize that, okay, it lies on the first quadrant, your theta will simply be arctan of the imaginary part. So quick comment, the imaginary part is whatever which is multiplying the I, and the real part is whatever which we are adding there. So if you plot your complex number and you realize that my A is positive and my B is also positive, it means it's in the first quadrant, then your theta will simply be the arctan of B over A. So that's done. So if you plot your complex number and you find out that it's in the fourth quadrant, on the fourth quadrant. So in the fourth quadrant, you will expect, you're looking here, your A should be greater than 0, but your B should be less than 0. So if your A is greater than 0 and B is less than 0, then clearly we're in the fourth quadrant. And your theta, which will give you is the right answers, is simply going to be the arctan of B over A. You take A as it is, and you take B as it is. B is whatever which is multiplying the I side. And your theta will be whatever value you get there. This is the fourth quadrant. And then quickly, we are now in the second quadrant. So second quadrant, your theta will be pi plus arctan of B over A. So these will always give you the correct principal value. So principal argument. So remember, the principal argument, all what we are saying is we needed theta, which is between pi and minus pi. So any value of theta which is outside this domain is gonna give us problems after some time. But if we can restrict our theta to this, life becomes really easy. So second quadrant, your theta is simply pi plus arctan of B over A. And you put the signs as they are. Put the B as it is, and you put the A as it is. So for the second quadrant, you will expect your A to be less than 0 and your B to be greater than 0. And then the last one, third quadrant. Third quadrant, your theta will be pi minus arctan of B over A. So if you plot your complex number when it's given in this form, and you realize that, damn, it's in the third quadrant, and how you are going to see is it's very simple. The third quadrant, your A should be less than 0, meaning it's negative, and your B should also be less than 0. So once you have a negative number here and a negative number here, cool, third quadrant. And how do we get our principal argument? Simply pi minus the arctan of B over A. You put the B as it is with the sign, and you put the A as it is with the sign. I hope that's clear. Okay. So let me take only this portion, because if you look at our problem, the A is negative and the B is positive. So which means we are on the second quadrant. So quickly to the next page, and we paste U here, second quadrant. Yep. And you can see that our A is actually -1 and our B is 1. Guess what? A is less than 0 and B is greater than 1. And we said all what we do is we'll say theta is simply pi plus arctan of our B is 1. That's going to be 1 over -1. So that's pi minus arctan plus, arctan of -1. I'm sure you guys know this from high school. We can take out the negative and then you have the arctan of 1. And quickly, something which we know, that's pi over 4. Pi over 4. Here we have pi over 2. So this is the 45 degrees triangle. It's 1, 1, square root 2. So arctan of 1, I can see from this triangle that it's pi over 4. So which means my theta is pi minus pi over 4, which I think it's going to give me 4 pi over 4 minus pi over 4. It's 3 pi over 4. So that's the angle which you were supposed to obtain there. And guess what? Obviously, this is between pi and -pi. Right? And we started this problem with the aim of writing our solution in this form. And our R, we obtained square root 2. It's going to be e to the I. Our power is 3 pi over 4. So fast forward, whatever which is inside the brackets, it is simply going to be equal to square root 2e to the I 3 pi over 4. This is all what you needed to do for this question. And then now it's going to be easy for us to introduce the power. It was 10. Unlike introducing it when it was like this, we can't multiply 10 brackets which are like this. Sure, you wouldn't be done even if you were given how many hours? 2. Yeah. But now this is an exponential form, so we know that we can easily introduce the power. So if you look at this guy, it's in the form a to the n to the power of m. This will simply be a and m. Right. So let's go back to the question now. We said -1 plus I to the power of 10. This is the same as we put whatever which was here. This is equal things which are inside the brackets. And this is raised to the power of 10. So yeah. Oh, I'm missing a square root 3 here. Sorry. I think there was a square root 3 and here plus I to the 10 negative. So even here I should have square root 3. Nice. So are we all still together? Because I'm not aiming at leaving anyone here. So if there's something which I did here which doesn't make sense,
I just
yes.
wanted to ask for the principal value or the argument. I just scanned over the memo, but did they award a mark for getting the arguments? Because I'm not sure.
Right.
And then I also wanted to ask if is a principal value of negative pi over 4 still correct?
Principal, no, it's not.
Oh,
It is
okay.
not. So do this. Follow. Just take this. What I wrote here. It's gonna save you from stress. See this
Okay.
table. It will always work out. Because you know what's the purpose of wanting the principal value is because we go to the next page. Just a quick comment and then we come back to this. So we all know that sine and these are periodic with 2 pi. Someone is there, mic on. Please mute yourself. Someone is saying, guys, please the correct link. Why do you want the link if you're in the meeting already? I'm just wondering. Yeah. Okay. So let me remove this. Right. So I was saying the reason why we are using the principal value is because we want to obtain the same answer. So we all know that sine and cos are periodical, the period of 360 / 2 pi. So if your friend gets an answer which is pi over 4, they can simply add 2 pi here. And this is gonna become, I believe, 9 pi over 4. And guess what?
What I was
This is
about is negative 10 of negative pi over 4 is the same as 10 of 3 pi over 4. So why is it wrong?
negative. You see now, this is why I was saying plot. So one thing you should normalize doing is plotting your complex number. Negative pi over 4 is in the 4th quadrant. Here. You are moving in the clockwise direction. It is here, negative pi over 4. And guess what? In this quadrant, your A value your Z is A plus IB. Your A value is greater than 0 and your B value is less than 0. And this is not the case for what you were given.
Oh, I see. Okay. So even though it's the same, it's wrong because of that.
Yes, because negative pi over 4 is in the fourth quadrant, and the values will not correspond. Your A is definitely not greater than 0 and your B is not negative. So please, and please again, just when you get your complex number, quickly draw your complex number in this plane. Then after you figure out, oh, it's in the first quadrant, then I know my formula for theta. Oh, fourth quadrant, I know my formula. Second quadrant, I know my formula. And the B and the A, you put them as they are. You don't omit the signs and try to do some high school maths. It's gonna give you a problem, a big one. So take the signs as they are, plot your complex number, see which quadrant it is on, and then take the formula and apply it, and you'll get the right things. Okay, cool. So fast forward.
Sorry.
Yeah.
Can you please do the principal argument of -1 minus I?
Okay, one. So let's see what that means. So it's -1 minus I. This is what you are saying.
Yes.
Okay, nice. So remember our previous form, A plus IB. So my A is -1, my B is -1. And guess what? This is in this quadrant. No, it's here. My A is negative here and my B is negative on this quadrant. So essentially, this is the same as X plus IY. Right? So X is -1, Y is -1. So we know X is -1 somewhere here, and Y is -1 somewhere here, and they meet here. And my angle there is gonna be, remember, he said this is the third quadrant after plotting our complex number. Third quadrant, we said our angle is always pi minus arctan of B over A or X over Y. So in this case, it's gonna be pi minus the arctan of -1 over -1. That's gonna be a nice +1. So essentially, you have pi minus the arctan of 1, which is pi minus pi over 4. Okay, wait a sec. Wait. Wait. Okay, so
I think you meant to say theta plus. Or-
yes, plus, it's a plus, it's a wait. Okay, let me quickly go to my diagram and see what I said here. Okay, so there it's a minus, and there it is a plus, minus, plus. Okay. Second quadrant, it's a minus. Okay, it's a plus. Okay, go here. My theta, pi, 4. Am I getting 3 pi over 4?
Sihle, you know, in that diagram, I think the mistake you made is at the second quadrant, it's pi minus arctan, and then in the third quadrant, it's pi plus.
Okay, let me go back and see. So you are saying I made a mistake here.
Yeah, over there. In the third quadrant, it's pi plus.
Okay, so here it is a plus,
Yeah.
and here it's a minus. Mm, mm. Did I make that mistake? Let me quickly think. No, because at the end of the day, scroll. At the end of the day, your theta must be between this and this. So if there's anyone who sees a mistake I made, please shout. Please. Shout if you see the mistake I made here.
I think you didn't make a mistake, but I don't know if you are allowed to put a negative on the 3 pi over 4 we got.
A negative on the 3 pi over 4 we got. So what do you mean? You mean here?
Yeah.
So what are you saying when you are saying you are not sure if we should put a negative?
Like we got 3 pi over 4. So
Yes.
we can just state the answer is negative 3 pi over 4, the argument.
Okay, so let me quickly go back. So you are saying from here,
Yes.
the pi is, theta is pi over 4.
No, we just put a negative on theta is 3 pi over 4, and then it becomes negative 3 pi over 4. I don't know if it's allowed.
No, it's not gonna work. Do you see why? It's because if now you are saying your theta is, so you are saying we should put negative 3 pi over 4.
Yeah, on the final answer.
Oh, okay, quickly. Some damage control. Forgive me. Now I see what mistake I made. Okay, so here it's okay. Quickly do the typical mistake. Okay. You see here, the third quadrant. It's supposed to be negative pi plus arctan of b over a. So essentially, my apologies, but it is a mistake. So theta in the third quadrant, our theta is arctan of b over a minus pi. This is the third quadrant. Silly mistake. Yes. Please fix my third quadrant here. So it's supposed to be arctan of b over a minus pi. Okay, fast forward, let's go back there. So the answer here was supposed to be, I'm supposed to have a positive here and a negative here, positive here, negative here. Our final answer is supposed to be negative 3 pi over 4. Negative 3 pi over 4. Yes. And if you think carefully, thing is, this is how I was able to figure out that I'm wrong. So we are in the third quadrant, and when we move from here to here, we are gonna move by pi over 4 is what, 150? Hope so. Yeah, we are gonna move by 150 degrees, but anti-clockwise. So one thing you should always ensure is that your theta is between pi and negative pi. So do the fixing for the third quadrant. Third quadrant is arctan of b over a minus pi. Then if you have this, it's always gonna work out. So as long as you have this, you can easily think around what the theta should be, but there's no need to think about such if already you have the diagram. So fast forward, this is the updated one, the third quadrant. I made a really dizzy mistake. Yeah, this is the right one. Does it answer the question of -1 plus negative I?
Yes, it does. Thank you.
Nice. Okay, fast forward, let's move, let us move to the next one. So the last or the final phase of your problem was to simply introduce the power of 10. Square root 2 e to the power of I 3 pi over 4. And then put in the 10 here. And remember that the square root is simply 1 over 2. So that's square root 3 multiplied by 2 to the 1 over 2. 10, and then if we introduce this 10 to these exponents, the answer we are going to get is it's 2 to the 5. It's 2 to the 5 multiplied by EI. That's going to be 30 pi over 4. Yeah. And then now, if you look at the question, yeah. So if you look at the question, they said find the principal value of the argument. So meaning this is now our new argument, which is that's 30 pi over 4. That's our new argument. Argument is simply the angle. Remember, it's nothing deep. So it's the angle. But immediately now, when they say the principal, it becomes something else. So principal, when they say principal, all what they are saying now is, okay, take that angle and work smart, make it such that it's going to be between pi and negative pi. That's all what they were saying when they were saying the principal. Because we have the argument already, the angle, but now they are saying they want the principal argument. So we should break this down until we find an equivalent angle, which is going to be within this range. Right. And one thing we know is to comment e to the I theta, it is simply cos theta plus I sine theta. And what do we know about cos and sine? What we know is that these ones, they have a period of 2 pi. So meaning if I say cos of pi plus theta plus 2 pi, this is still gonna give me cos of theta. Same way I have sine of theta plus 2 pi. This is just gonna give me the same answer as sine of theta. Right. So let's break this 30 over 4 to some addition of 2 pi's and see how it goes. So I have 30 pi over 4. So what is 30 over 4? 30 over 4, I think I'm gonna get 15 pi over 2. Yeah, cancel the 2's. And then I can simply write this as, let's see, I can write it as either 14 pi plus pi over 2, or alternatively, I can write this as 16 pi minus pi over 2. Are we still together?
Yes.
Yes.
Okay. Nice. So we said what we want to do is we want to get theta plus eventually something like 2 pi or 2 pi k. So yeah, you guys know this. And if we put in sine and cos, the answer is simply going to be theta here. Right? And this theta which we want, we are going to be more than happy. This theta is between pi and minus pi. So if I look at these two forms, if I look at this one, okay, let's try it out. So 14 over 2, if I split those things, it's going to be 7 pi plus pi over 2. If I look at this part, it's not doing the things which need to be done. Right. So I'm like, okay, equally so, let me try this one now, see what it gives me. So 16 over 2, that's going to be 8 pi. Minus pi over 2. Okay, so I know I'm dealing with sine and cos. So this is simply the same as 2 pi k. 5 cos of theta plus 2 pi k. This is simply the same as cos of theta. 5 sine of theta plus 2 pi k is the same as sine theta. So if I look at this one, I'm like, okay, this is a multiple of 2 pi. So this is out. I'm left with this. Now the question I'm going to ask is it between pi and negative pi? And then obviously the answer is yes. Hence, my theta is simply negative pi over 2. And that's the principal argument. Yeah, so who did I lose? So unmute yourself and tell me where you got lost. Yes.
Can you please like re-explain, like go over it again?
Okay, nice. So please look at the screen. So previously you do understand how we got to 30 pi over 4.
Yes.
Nice. Do you agree that 30 pi over 4 is the same as 15 pi over 2?
Yes.
Cool. And do you agree that 15 pi over 2 is the same as 14 pi plus pi divided by 2?
Yes.
Okay, nice. Do you agree that this is still the same as 16 pi minus pi divided by 2?
Yes.
Okay, nice. And do you know that cos and sine are periodical with a period of 2 pi?
Mm-hmm.
Nice. So if I'm dealing with sine because I'm dealing with e to the power of something. And remember, the e to the power of something, it translates to a cos and a sine.
Yes.
Right. So do you agree that if I'm dealing with the cos and the sine, if I say cos of theta plus 2 pi k, I'm going to get the same answer as when I'm saying cos of theta only.
Mm-hmm.
Okay, cool. And previously I said the principal argument is the angle. It should be between pi and negative pi. You get that part?
Yes.
Okay, nice. So then I said, cool, let's look at this expression, the one with 14 pi plus pi over 2. Let's break it down. So if you divide the 14 by 2, you get your 7.
Mm-hmm.
And the When I divide to the pi and you get this answer as a whole. Did you get that part?
Yes.
Cool. Then we come back to the one with the 16. When we divide the 16 with the 2, we get 8 pi minus the pi over 2. Do you get that part?
Mm-hmm.
And then I said from metric, we know e to the I theta, well, we don't know this from metric, but e to the I theta, it's simply a combination of sine and cos. You know that cos of theta plus 2 pi k is the same as cos of theta, isn't it?
Yes.
So meaning essentially, if you have 2 pi k, meaning a multiple of 2 pi, you can simply ignore that part and take the theta.
Oh.
Right. And then I went straight to this and I'm like, okay, this is a multiple of 2 pi. Where k, if you look carefully, k is 4. Doesn't matter what k is, but I'm dealing with sine and cos. I'm going to ignore this and take this angle. But now the question which I'm going to ask afterwards, after taking this angle, I'm going to check if I need to do further work. And the question is going to be, is it between pi and negative pi? If it is between pi and negative pi, I'm done. Lucky enough for this problem, it is between negative pi and pi. So hence, the answer is that.
Okay, thank you.
I have
Okay.
one last thing for this question.
Yes.
You know when you got the original principal value of 3 pi over 4, how does that apply with the change in the diagram you made? Because with the change that you made, it would now be pi minus arctan, and yeah, so I don't know how you get 3 pi over 4 now with the adjusted diagram.
Can you please repeat your question again?
Oh, sorry. You know how you adjusted the diagram?
Mm-hmm.
Yeah, so when you adjusted the diagram, you didn't adjust the results of 3 pi over 4. How come?
When I adjusted the diagram, I did not adjust the result of 3 pi over 4.
That's the original principal value that you got.
You mean the initial one?
Yeah.
Yeah, and what's up?
If you change the diagram, then it's pi minus arctan of -1. So if you take the -1 out, then it's pi plus arctan of 1. That's pi plus 3 pi over 4. If you go,
Oh, okay. So you are still here.
yeah.
Okay. No, it's not gonna be the plus. So you see the calculation I did, it still holds. So we are in the second quadrant. It's 1 divided by -1 here. You agree?
Yeah.
And then that's gonna be arctan of -1. And we can simply pull out the negative.
Oh, okay. So you still left it as pi plus. Is the second quadrant still pi plus?
Yes. So the only adjustment was on the third quadrant. I made a really simple mistake.
Okay.
They
Okay.
still hold.
Yeah, I see. Thank you.
Cheers. Let's move. So is there anyone who has a question with regards to this? So the takeaway from this is when you do your complex number, plot your complex number, and then when you now know which quadrant you are dealing with, simply refer back to your notes, which for your exam the notes need to be in your head. Then you refer to your head, and your head will tell you that, okay, cool, you're in the first quadrant, you don't do any funny addition and subtraction, you take things as they are. Fourth quadrant, you don't do any funny addition or subtraction, you take things as they are, and then it's the second and third quadrant which needs some special attention. So I hope you take this down. So next page.
Sorry.
Yes.
So suppose -pi over 2 is not in the range -pi to pi. Are we allowed to repeat the same procedure we did for 30 pi over 4?
Yes, you are. So, for example, let's say, you see the part where I have 8 pi plus 8 pi minus pi over 2. So I'm just going to make a quick example. Let's say after doing that, we had 8 pi plus 3 pi over 2. So I was going to be like, okay, cool. Okay, we are going to discard. Our theta is simply 3 pi over 2. But now the question is it between negative pi and pi? No, it's not. So 3 over 2 is greater than 1. So that's like 1.5 pi. So I'm going to take that again and say, okay, cool. 3 pi over 2, this is the same as 2 pi plus pi over 2. Or alternatively, someone can come and say, let me see. Someone else can come and say, let me see, should I say 4 pi minus pi over 2? Yes, someone else can come and say this. This is interesting. And then here, you're going to have pi plus pi over 2. This doesn't look nice. But here, we are going to have 2 pi minus pi over 2. I'm just going to say, okay, here's a multiple of 2 pi k. Then my theta should be negative pi over 2. Does this answer the question? So if we stopped here, I was going to take this and then redo the steps again until I get here. If this still didn't fit, I was going to take this and work again. Does it answer the question?
Yes, it did. Thank you.
Can I ask something?
Yes.
So is it ideal to make sure that you always have the pi being a multiple of 2 so that it can cancel out?
Yes. I think that's another way to think about that. So I think what you are
If
saying
it's
now,
not a multiple of 2, then like how do you do it?
I think you see the trick is you choosing a smart form, because you can always make it a multiple of 2 by just changing one thing, the sign, and adding something, because we have 2 forms. So look at this. One can come and choose this. This is not gonna make your life too simple. But a minor difference and say, okay, let me make my 3 to be 4 minus 1. I know here I'm gonna have a multiple of 2 when I divide, and then it makes life to be simple. So you do the choices in real time when you write the exam, but make sure your choice doesn't complicate your life further, because these people will not award marks because you had many steps, of which some of them you could have avoided. So,
Okay.
so let's quickly go to question 2. So is there anyone who wants to do question 2? If anyone wants question 2,
Yes.
Okay, nice. Power. What's up? Okay, so let's see question 2. I'm gonna run over question 2. So partial fractions. This is nice stuff. It is full stuff. You think about it. So I'm tempted to say I'm gonna leave this one for homework. So I'm not gonna do. Should I? I'm thinking of doing this question.
I don't mind because I'm the only one that asked. So if you just run over the theory behind it, then I can see you later on.
So I'm not gonna do the question, but I'm gonna say, okay, partial fractions. So under partial fractions, there is something they call simple poles. So simple poles. See, poles are whatever which you find on your denominator. Yeah. So those are poles. Whatever which you find on the denominator are poles. So when we say simple, all what we are saying is all the poles, we have no repeated poles there. Repeated. Or we have no square or cube there. We have no pole which is to the power of something. Right. So a pole would be, for example, z minus a. We don't have z minus a to the power of anything, where n can be greater or equal to 2. So if you have simple poles, meaning you have no square on one of the poles or whatnot, then we can use what we call the heavy side to break down this thing. The heavy side formula. So all what that formula entails is, let's say you have a fraction, I'm gonna call it h of z. And that fraction on top, it is a function of z. And it is divided by g of z. So as long as here on g of z, we do not have any repeated poles, then we can use the heavy side. And the heavy side, all what they say is, let's say for example, I have f of z over z minus b, z minus a, and z minus c. This is in the denominator. I'm gonna take this to the next page. Okay, let me take the bigger portion. So just follow with me. You should be able to do that problem. Paste here. Okay. So this thing is in like copy. Okay, so if we use partial fractions, you see our h of z, at the end of the day, we're expecting h of z to be, let's say after factorizing the denominator, we're expecting a over z minus b plus capital letter B, which is some constant, over z minus a plus capital letter C over z minus c. And how you get your a, just note this down. Change the font so you can zoom in. So how you get your a is you go to your original expression, this one. So this is after factorizing your denominator into simple fractions. Simple fractions, it's simply z minus whatever times z minus whatever. So how you get your a? Look at your a. Your a is on top of z minus b. So now go to my original expression and say, I'm gonna cancel out z minus b. And what I'm gonna be left with there is f of z over z minus a times z minus c. And then this a is on top of b. So where there is z, I'm gonna put b. Then whatever I get after plugging in the b on the top function, which is some function, and plugging b here and here, that's gonna be my a. And then equally so, let's look at b. So b, if you look at b, b is on top of z minus a. So I'm gonna go to my factorized original expression and say, okay, So z minus a, I don't need you here. I remove z minus a. And the expression which is left is f of z divided by z minus b and z minus c. Since I'm looking for what is on top of z minus z, I'm gonna put a. And then where I see z in that expression, I sub a, and the answer which comes out is gonna be my yeah. And then lastly, c. C on top of z minus c. So I'm gonna go to the original expression which I've factored out. I'm gonna cancel where I see z minus c. And what is left is f of z over z minus b, z minus a. Then since I'm looking for what is on top of z minus c, everything which is z here, I'm gonna substitute it by c. That's how you do this problem. I'm not sure if that answers this. So you'll go and do the dirty work here, but that's the principle behind solving this problem.
I'll do that after this session.
Just do it and then tell me a message if you have my numbers.
Okay, thank you.
Yeah. Okay. So let's see question 3. Question 3. So let's see what's going on there. Was the most interesting one for this one. Question 3. So question 3, you were given what? Factorize z to the power of 4 plus 81 into real quadratic factors. You know, that real really matters. So I'm just gonna write down, I don't know for what reason. I'm gonna write this like, okay, they need some real stuff. You don't do fake slash imaginary. Suppose to factorize z to the 4 plus 81. Okay. Okay, let's see. Okay, so the first, what they're expecting us is to have the factors. You guys know what factors are. We need to write this in this form. So the first thing we can attempt to do is obviously equate this to 0. Then when you equate to 0, you will solve for the 4 z values. See, when I say z, when I say z to the 4 plus 81 should be 0. So essentially, I am saying I probably have 4 values of z which I can sub in there and add with 81, and the answer I'm gonna get is 0. So I'm gonna look for those z values, those 4 z values. And z minus d. I'm gonna look for these values, right? That's what I'm looking for. And then these are just gonna make my factors. Okay, cool. So fast forward, it's z to the 4 plus 81, that's 0. Then z to the 4 is negative 81. And this is my favorite. You should know your complex numbers. You should know your complex numbers. So if you come here, let me use another line, this one. If I come to my complex plane, this is the real axis, and the vertical one is the imaginary axis. So I can see that, you see this 81 on these axes, negative 81 is here. Because 81 is the real part, it is real. And since we have no I plus something, it means the imaginary part is 0. It means the imaginary part is just in this line. So negative 81 is there. And guess what? It is This is so nice. What is the angle here? So remember that the angle, we always measure the angle relative to the, what you call, relative to the positive x-axis. The angle, we always measure it like this. But either way, it's going to be the same for this one, because even if you come in this direction, okay. But standard, we usually come from 0 and then go to here. So we can see that actually we moved from an angle which is 0 to an angle which is 180/pi. And now I'm going to write this as in let's see, I'm going to write this in modulus argument form, right? Because this is still like a complex number, still like z is a plus ib. Now I want to write it as re to the I theta. So I can see that actually what I have here is plus 0. So if you think carefully, my r is going to be the square root of 81, negative 81 squared plus 0 squared. And the r is going to be 81. And my theta, as we saw, it's just going to be pi. You know, so I'm writing this in modulus argument form because I'm introducing a power. And I know powers are easy to deal with when we have a form which looks like this. That's why I'm even stressing about writing this negative 81 as in modulus argument form. Okay, so let's move to the next page. And you can also do some checks. So look, I'm saying negative 81 is the same as 81 e to the I pi. So you can always do some check if this is the case. So we remember that e to the I theta is cos theta plus I sine theta. So which means actually what I have on the right is 81 times cos of pi plus I sine of pi. And just quickly, you remember your graphs. The sine looks like this. 2 pi here, it's pi there, and your cos graph looks like this. Amplitude shouldn't be. The cos graph looks like this. Right. So cos of pi is here. Cos of pi is -1. So we have 81 times -1 plus sine of pi. The sine graph is the red one. And sine of pi, it is at 0, so plus 0. So the answer indeed, 81 times -1, it's -81. So me writing 81 in this form, I'm not doing any magic or any scary things. More like I'm writing it in another form, which is going to be more convenient for me to work with. So fast forward, we have z to the 4, we have 81 to the I pi. Yeah. Okay, cool. And we know that this is periodic with 2 pi. So this still holds. Sine and cos are periodic with 2 pi. So this is nothing fancy. And then now if I take my z to the 4, now I'm solving for the z. What I do on the left, I should do on the right-hand side. Plus 2 pi. Okay, close. That's 1/4. Right. So if I do the maths here, 1/4 e to the I, I'm gonna have pi plus 2 pi k over 4. And this one is gonna be 3. And the reason is this. So 81 is 3 to the 4. We are now raising this to the 1/4. Other part is just gonna be pi plus 2 k over 4. Yeah. So pick 1, 4, and 4, they cancel. Our answer is a good 3 here. Then now we need to deal with the exponent part. Okay, so let's see how we do the exponent part. Let me copy the last part. Copy. So I need you to think with me on this one. Right. So I'm gonna write the angle down. Okay, so what we have here is we agree we have 3e to the I. Yeah. Now this is what I need you to focus on. We have pi plus 2 pi k over 4. So we now need to decide on k values. So let me focus on the exponent because it's the key part. This is too big. Okay. Oh, I was looking for this one. Sorry. I have pi plus 2 pi k over 4. So just pause and think with me. So because I'm taking the nth root here, which is 4, that means I should have 4 solutions. More like I should choose 4 k values. Right. And we don't just decide on the k values because that's what we like and it's like it's gonna work. It doesn't work. So you need to decide on the k values carefully. And my comment is, you see, when we decide on the k values, whatever k value we put here, the outcome or the angle we get, it should be between pi and negative pi. Any k value which will give you an angle which is outside this, you do not take it. So meaning we will choose our k value such that whatever angle we get when we put that k value, it's gonna be between these magic numbers, pi and negative pi. So obviously 0, it looks like it will always work. So for k is 0, the angle above here will be
Sorry,
pi. Yes.
So it's not that when we choose the values of k, we look at the highest degree of
Of
the power, which is 4.
yeah, and then you take the square root. Okay,
Yes.
yeah, okay, good.
No, I think you go 0, 1, 2, 3. Yeah, 0, 1, 2, 3, 4, like that.
Okay, so let's hear what she has to say first, and then I'm gonna go to you. You can shoot.
I think it's yes. I wanted to say the same thing as him. Since the highest degree is 4, so which means that we're gonna choose. Which means it has 4. I don't know if it's gonna be 0, 1, 2, 3 or 0, 1, 2, 3, 4.
Oh, so you choose those.
Yes.
You know what's the problem with those?
No.
The problem is it's gonna because I saw your memo. You know, the problem is it's gonna need you. You see what we were doing when we wanted the principal argument.
Mm-hmm.
It's gonna need you. So let's say, for example, your lecturer. Let me quickly check. So at K is 3. K is 3. The angle you get is 7 pi over 4. And guess what? You need to, again, if you look at your memo, do the dirty work of getting the smallest value, which is the principal value. So 8 pi minus pi over 4, that's going to be 2 pi minus pi over 4. As previously argued, you discard this and your answer becomes negative pi over 4. So at Z is 3, the angle they got is negative pi over 4. But me, I'm saying, look, we can easily avoid this step, which is going to need us to do what we're running away from. Because if here, someone else decides to say, okay, I have 7 there, so this is the same as 6 pi plus pi over 4. This is not going to work nice on them. So me, I'm saying, look, you can avoid, because this, you cannot work with this answer. Eventually, you need to take it here. And guess what? When you take it here, all what you were doing is doing the dirty job of ensuring it's between pi and negative pi. So me, I'm saying, look, you can avoid this step. You can avoid this step and this one by choosing your K values carefully. Because it is not the K values which will give you the correct mark, but it is your answer, your Z value, which will give you the correct, which will give you the mark. So if you look carefully, it didn't give a mark for you choosing your K values. Right. So fast forward, let me get back to what I was saying here. Right. So I was saying, look, so let's look at this angle. If I put in K is 0, I'm gonna have as my angle pi over 4. Nice. If I put in, let's see, if I put in K is 1, I'm gonna have 2 plus, I'm gonna have what? 2 pi plus pi, that's gonna be 3. I'm gonna have 3 pi over 4. If I choose K is negative 1, okay, let's go up. Let me choose 2. If I choose K is 2, I'm gonna have, let's see, 2, that's gonna be a 4, 5. I'm gonna have 5 pi over 4. Okay, I'm gonna pause a bit here. Like, okay, this exceeds whatever which I'm looking for. Let me quickly go below 1, below 0. If I choose K is negative 1, I'm gonna get, it's gonna be 2 pi times negative 1 plus pi. I'm gonna get negative pi over 4. Okay, so let me try negative 2. If I choose K is negative 2, I'm gonna get 2 pi times negative 2. It's negative 4 plus 1. That's negative 3 pi over 4. Okay, I'm like, nice. So this one exceeds what I'm looking for. It's out. And guess what? I have my 4 values here. This is between negative pi and positive pi. It all works. So I was avoiding doing the same thing we were doing previously of saying, okay, you now have 7 pi over 4. You now need to find the principal value of this angle now. It's 8 pi minus pi over 4. You do what we were doing previously. So I'm saying you can look at your angle, take it down the same way I did, and plug in the values and start with 0 and then say, okay, 0, it works. Try 1, it works. You try 2, okay, it no longer works. So let me pause here. Let me go below 0. Try negative 1, it works. try -2, it works. I was looking for 4 values, so I paused. These are my angles. Does it make sense?
Yes, it does.
Nice. So I'm done. There's no need for me to have many steps. And then all what I do now is I'm like, okay, so now we have our key values. Let me copy them quickly. Yes. Go to the next page. So you can avoid a number of steps by making smart choices in codes. Okay, nice. So essentially now I can go back and be like, okay, so my Z0 is, remember we had a 3 there, it's 3 e to the I pi over 4. That's at k is 0. My Z1 is e, it's 3 e to the I 3 pi over 4. My Z minus 1 is e to the I negative pi over 4, and my Z minus 2 is simply missing a 3 here. Z minus 1 is 3. 3e to the I negative 3 pi over 4. Okay, nice and cool. And then all what is left here is for me to write this in vector form. So in vector form, how it's going to look is Z minus your Z1, Z minus Z2, why we don't have Z2, Z minus Z0, Z minus, we have Z minus 1, these are subscripts, minus 1. Z minus, I have 1 is minus 2. These are the factors which I was looking for, right? And then all what I do now is I substitute here. So at 1, I have, let me take this, I have 3e to the I pi over 4. So that is at 0. Okay, I'm just going to substitute those vectors. The order doesn't matter, but as long as you have z minus that vector, 3e to the, let's say, minus pi over 4, and you have z minus e to the I 3 pi over 4, and lastly we have z minus e, missing 3's here, missing a 3 here, and a 3 here, I negative 3 pi over 4, and then we close the bracket out by space. And then one thing I want to bring to our attention is, look here, you see this complex number in this one, they are conjugates of one another. Look at this complex number, look at the angle, look at that one. These ones use different colors. Pink ones conjugates of one another, and the green ones are conjugates of one another. So I'm gonna quickly remind you of something. So if Z is E, if Z is RE to the I beta, the conjugate of Z is simply RE to the negative I beta. This is the conjugate. So hence I'm saying, if I go to the side, I see that these are conjugates of one another, because here the angle is pi over 4, here it's negative pi over 4. Here it's 3 pi over 4, here it's negative 3 pi over which is exactly what I have this side, conjugate. And so essentially that side, we have something like Z minus, let me call it ZA minus ZA conjugate multiplied by Z minus ZB multiplied by Z minus ZB conjugate. So something you should remember is that when you multiply Z and Z minus, okay, let's remove the conjugate from this one, and Z minus ZA conjugate, the answer to this is Z squared minus 2 times the real part of Z times Z plus the mod of Z A all squared. You guys remember this? Right. So if you don't remember this, then yeah, take it as a statement. So how this comes about essentially is you do your FOIL. Do your FOIL. Quickly, your FOIL is gonna give you Z squared plus, you'll have Z ZA dash minus Z ZA plus you'll have ZA dash. And then one thing you should be aware of is that Z times Z dash is the mod of Z squared. So this was given under properties of complex numbers, and Z and Z, where Z is a complex number plus its conjugate, is simply 2 times the real part of Z. So if you look carefully here, I can factor out Z and be left with Z squared minus Z. Now I have ZA dash plus ZA plus I have ZA dash. Here I'm gonna apply this rule that ZA times ZA dash is simply gonna be the modulus. Nice. And then here I'm simply gonna use this. So hence I said the answer to here is simply that. And how this comes in is, you look at our expression, the side. I hate it because now the sound is so long and I hate. Okay, Steve. Let's paste here. Let's see what. Paste. Yeah. Right. So if you look carefully here, this is Z minus a conjugate, Z minus a conjugate. And guess what? The real part of e to the I theta is simply cos theta. And the imaginary part of e to the I theta, I'm sure you can agree, is sine theta. So fast forward, if you do the maths here, the first bracket will give you Z squared minus Z times, or 2Z times the real part of 3e to the I pi over 4. Then plus the modulus of this thing is just going to be 3, but the modulus squared is going to be 9. And then we do the same the side. I'm going to pause now for equation, the real part of 3e to the I 3 pi over 4 plus 9. Let me quickly simplify this. Minus 2z times 3. The real part of e to the I pi over 4. That's going to be cos of pi over 4 plus 9 times z squared minus 2z times 3. Then cos of 3 pi over 4 plus 9. Yeah, so I'm gonna pause here and take a question. If there is any questions, that's gonna be here. So yeah, that's 9 z squared. Okay, it's gonna be a plus 6z over square 2 plus 9. Okay, so I'm gonna pause for any questions. So this was supposed to be your final answer. So I'm gonna pause. Who did I lose and where? So just shout if I lost you somewhere.
I just got lost towards the end of the last page. I just couldn't.
Me too.
Okay. Oh, okay. Let's give it a shot again. Right. Did you see the part where I was saying, let's say we have a complex number at A.
No, it's not that I got lost. I just couldn't keep up. I just wanted to go back to see what you wrote.
Okay. So let's see. You do understand how we got here, here,
Yes.
here. So who erased my I and 3 pi over 4? Okay, nice. And then you do know this and this.
Yes, I know that. I also understand the conjugates that, so with the identification of that, but it was I think how you multiplied in all those rules that you wrote down. I just want to look at them.
Okay. Nice. So let's look at, I'm gonna pause just here. It's here. So look at this. So look at what I said here. I was like z minus za multiplied by z minus za bar. Bar simply means the conjugate. This is the same as z squared minus 2 times the real part of z times z plus the modulus of za all squared. Did you get that part?
Yes, I understand that.
Okay, nice. Next page. So if you look carefully, my za is this. The za bar is this. So I'm going to have z squared minus 2z times the real part of za, and za is 3 e to the I pi over 4. And then plus, if you remember from the previous page, the modulus of z squared. So when you take the modulus of this, remember the complex part becomes 1, and then you are left with the 3, and you square that 3 and it becomes a 9.
Okay. Okay,
and then we do the same for the second part. So my z b is this. My z bar b is this. And we said z squared minus 2z times the real part of this complex number. And the real part, we said the real part of e to the I beta is simply cos theta. Our theta in this case is 3 pi over 2, 3 pi over 4. And the 9 is simply the modulus of this complex number. And the thing with the e to the I theta, it always becomes 0, that part. So essentially we have 3 squared, which is 9.
Okay.
So if you lost.
Yeah, follow.
Okay, nice. Okay, fast forward. Let's see the last question for question 4. So it's a nice test. Question 4. Let's see what's going on there. Okay. The summation from 0 to infinity, 6 to the n, and that. Okay. This was very simple. It wasn't simple, it was interesting. Okay, let's see. So we are summing from 0 to infinity. What we are summing is 16 to the power of n multiplied by sine of 3 pi. Okay, why am I thinking of 3? Sine of n pi over 3. This is all divided by 2n factorial. Okay, nice. So the first thing we should do here, which is going to make our life to be simple, is we cannot sum sine. Instead, we can make it to be an exponential order. And how you do that is easy. So e to the I theta is cos theta plus I sine theta. And the real part of e to the I theta is simply whatever which is not multiplied by the I, which is cos theta. The imaginary part of e to the I theta is whatever which is multiplied by the I. In this case, it's sine theta. So meaning essentially you can write sine theta as e to the power of whatever you see in the theta, but you should put the imaginary here, and these will be equally valid. So we can replace sine theta by e to the I theta, and then we put that we are looking at the imaginary part of that, and it's going to be valid. So hence, I can simply transform this expression above to, I can say this is the same as this, n is 0, 16 to the n. I can say this is the case I, n pi over 3 over 2, that. Yes. And then because the rest of the numbers, 16 is a real number and n is a real number, I am allowed to put the imaginary sign outside and encapsulate everything inside. So I have 16 to the n, e to the I, n pi over 3 over 2n pi. So this is nothing new and nothing complicated. So what we can do here is we can see we can make a common power and take out the n when you look at these. So essentially what we have there is simply a to the n times b to the n. Okay, yeah. So you can simply have ab to the power of n. That's what I'm gonna do. Okay. I hope this will not catch up. Unity 0. So I have 16 e to the power of I over 3 to the power of n divided by and tutorial. And yeah. Yeah. Let me take this and move with it to the next. Okay, before I move, am I losing anyone? Are we losing anyone before I move? Okay, so I'm gonna assume the answer is no. It's okay. Copy this. Okay, so nice and clean. So now the question is, what am I gonna do with this expression, because it doesn't look even nice, doesn't it? So you need to remember your what you call, I think this is even somewhere on what you call read view. The sum, it's crazy that you need to remember these things, but I'm gonna assume you were given from any zero. If we are summing, I think my students should know this. I remember there's a problem which we did on, it was in the charts. It was like this. The answer to this is simply whatever which is there. It's the Z. Just check your type questions. They made you to do this. I remember. You see now the benefits of doing your type questions. So someone I did the type questions with should remember that we once did a problem which was like this. And whatever which is here, as long as the exponent is 2 and we are dividing by 2 pi, the answer will just be hyperbolic cosine of whatever which is inside here. So you did your third questions, I'm sure you're going to be like, wow, it's coming back. So which simply means fast forward, we need to try and be smart inside here so that we can use what we know. So make sure you do your third questions. That's my comment, because this is literally from the third questions. So we need to factor out a 2 inside here. And we factor out a 2, we are going to be left with 4. That power, it's going to be pi over 6 now. And that's going to be 2n divided by 2n factorial. Yeah. And finally, what is inside is just going to translate to just like what we saw here. Just take what is in the bracket and put it where there's cosh. And what is inside there is simply 4e to the I think I'm missing an n. Yeah. To the I n pi over 6. Yeah. So these are the benefits of doing your calculations. Crazy. Okay, and then fast forward, let's simplify this. So I have cosh of in brackets I have 4 times 8. The n is not here. My mistake. Move the n here. Easy. So I'm gonna have 4 times cos of pi over 6 plus I sine of pi over 6. So here I'm not doing any rocket science. E to the I theta is cos theta plus I sin theta. That's what I'm doing here. Our theta is pi over 6. Okay, copy, let's go to the next page. Okay, I paste here. Paste. Yeah. And then from here you can do your maths. Okay, so I'm not gonna finish this up. I think, let me see how much I can do. Pi over 6, that's 30, pi over 3. If I remember well, that's 1, 2, square root 3. That's pi over 2. So what we have there is the imaginary part of 4 times cos of pi over 6. That's square root 3 over 2. Plus I sine of pi over 6. That's 1 over 2. Oh, there's cosine inside. Yes.
Sorry, is that your special angle?
Yes.
Triangle. The pi over, it's not the opposite of pi over 3. That's 1, and then pi like the square root of 3 on the other side.
No, I don't agree. Yeah, I think you made a mistake there. Pi over 3 is 60 degrees. Pi over 6 is 30 degrees. So 30 should be faced to the side which is a bit smaller. 1 is smaller than square root 3.
Okay.
Cosh of square root 3 over 2 plus I 1 over 2. Okay, and then you guys, I'm sure you know that cosh of, let's say something, cosh of x, that is the same as e to the x plus e to the minus x, all divided by 2. Right. So fast forward, I'm going to have 4 times e to the square root 2 square root 3. Square root 3 over 2 plus I 1 over 2 plus e to the negative square root 3 over 2 plus, plus I over 2. And then from here, I'm going to leave it upon you to do the dirty work. So you will expand here. You'll have the complex part, which you will get here, the imaginary. So you do the expansion here. You will eventually use e to the I theta is cos theta plus I sine theta. And you will look for the part which is multiplied by the i's. So let me take you halfway, and then we need to go to calculus. See. I should have a square root here. Square. Okay, nice. So imaginary part of, I'm going to have 4 e to the square root 3 over 2 times, I have a 1 here. This is more like theta. So essentially I have cos 1 over 2 plus I sine 1 over 2. And then, yeah, close that part. And then plus 4.
Sir,
yes.
sorry, sir. I don't know if it's me, but I cannot see what you are writing on your page.
Yeah,
Okay.
same here.
So you can no longer see my screen.
Now we can see it.
Okay.
There we go.
Weird stuff. Sorry. Let me see here. I'm gonna have cos of negative 1 over 2 plus I sine of negative 1 over 2. Okay, so just check and see if you follow what I did here. I'm just hoping I made no mistake because yes.
Sorry, sir, but I'm a bit lost.
Mm.
The part where you change the kosh into the EULA identity, I don't know if it's me, but is this supposed to be like, is the whole thing isn't it supposed to be divided by 2 or something?
Yes, you are right. So that's what I'm noticing now. I'm missing a 2. Let's put it here. And let's put it here. Does it solve the problem? Yes.
Thank you.
Yes. And then fast forward. Now we are going to look for the imaginary part of the solution, meaning whatever which is multiplied by the I. Okay, cool. So I'm gonna come here. So this is okay. Let me make this to be a 2. Let's make it to be a 2. So here I'm gonna need you to follow. Now we want the imaginary part of whatever which is inside. The imaginary part is whatever which is after the I. So if I multiply this and this, I'm gonna get the imaginary part, which means one part of the imaginary part will come from 2e to the square root of 3 over 2 times sine 1 over 2. Right. So that's done with the first bracket. Second bracket, I have this outside. And inside, I have this. So essentially what I have is plus 2e to the negative square root 3 over 2 multiplied by sine negative 1 over 2. Right. And if you look carefully, 1 over 2, if you look here, we can factor out this negative. And then all what this is going to be is e to the square root 3 over 2 sine of 1 over 2 minus 2 e to the negative 3 over 2 sine 1 over 2. And then if we factor out the sine of 1 over 2 here, what is left inside is e to the square root of 3 pi over 2 minus e to the minus square root of 3 pi over 2. So this looks like hyperbolic sine, but the only thing which is left is the division by 2. So I'm going to introduce a 2 here and introduce a division by 2. And this entire bracket and what is on the left is going to transform into hyperbolic sine. So let's see. Okay, let me copy that part. This is interesting. Copy. Paste here. Nice. So this will transform into hyperbolic sine. Hyperbolic sine, remember, beta is simply e to the beta minus e to the minus theta over 2. And in this case, we can see that actually our theta is this. So this becomes 2 sine 1 over 2 hyperbolic sine of square root 3 over 2. And this is my final answer. Yes, and then I'm gonna wait for comments because I'm sure someone is like, wow, this is crazy. Okay, so any comment?
Sorry, can you please go to the previous page?
Okay, so let's see. Yes, we are here.
No, I can't. Yeah. So where did the 2 go on the second from last statement?
Second last statement.
Yes.
Okay, so let me see which 2. Are you talking about this 2?
Yes.
Okay, so let me see what I do. If I introduce okay, it's gonna be a 4. Nice. So it's gonna be 2 times 2. Typical mistakes. Are you okay?
Yeah.
So
And
that's the yes.
can we go to the last one?
Yes, here.
Yeah.
Mhm. So I'm missing a 2 here. What else is missing?
I think it's okay now. Thank you.
Okay, thanks. So my answer has a 4 here. So this is my answer, and yeah, I'm gonna wait for someone to say something.
Sorry, but I'm still a bit confused by the math. Uh,
Where
there
are you
was
looking?
no, so uh, there was no 1/2. So I mean, like what we had when we took out the 2 sign half, we just had e to that minus e to the minus that. We didn't have an over 2, and I'm assuming we're the ones who introduced it, right?
Yes, you mean this to the blue one?
Have hyperbolic sign.
Yes, because we know hyperbolic sign has
Yeah,
this.
it has over 2. So
Mhm.
just on the next slide, can you please go to the next one?
Can you see the next one?
So no, okay, now I can see it. So my thing is we introduced the 2 ourselves, and because you just added a 2, so this was for before. Is that 2 supposed to be like, because if you're gonna divide by 2, shouldn't you also multiply by 2? Because there was no 2 in the
Yes,
first place.
that's what we did here.
Oh, so that's okay. Thank you. Now I understand.
Yes. So is there anyone with a question? If there's no one, I think I'm gonna leave B to you guys. I don't know. What is the question 5? Yeah. So if no one has a question here, then we can proceed. It's so interesting. Yes.
Susan,
Yes.
do you mind like giving us a brief of like complex logs in 5 minutes?
Complex logs. Let me see. So you guys should really look at what I do carefully, because one mistake, then in fact I did make a mistake, but I'm not gonna fix that mistake. It's for you to spot when you are looking at when you are watching this video and looking at it. So I made a mistake somewhere. I see now. Okay, let's fast forward. Mistake by a factor. Okay, complex logs. By complex logs, do you mean the length of a complex number?
Yeah, those things.
So, you know what? This is the easiest thing. Guess what you need to do? You see this Euler thing. It will always hunt people. So this is the easiest thing. So the first thing you need to do is to make your life simple. You can just simply take this a plus ib, make it to be e, make it to be re to the I beta. And we've covered how we calculate the r, how we decide on your beta, right? And then after making it to be in this form, we know that our r is simply the mod of z. Yeah. So let's say this is z. So what you'll have is ln of RE to the I theta. And remember your log laws. It's the quick one. Ln of AB is the same as ln of A plus ln of B. And ln of A minus B, okay, ln of A divided by B. It's ln of A minus ln of B. Right. So using these ones, we can see we are multiplying R and E to the I theta. So we have ln of R plus ln of E to the I theta. Right. And remember, ln of E to the P is simply going to be P. Right. This looks really weird. Let me rather say ln of A to the B is B, ln of A. But ln of E is simply 1. So fast forward, what we have there is ln of R, we know it's the mod of Z, plus we'll have I theta here, ln of E. This is 1. So essentially, when you take the ln of a complex number, all what you need is the modulus of that number plus the theta. And this is plus, we know we can always add multiples of 2 pi a. Right? So this is what I have to say. And then fast forward, for the problem you were given was, so you were given ln of 2i. So essentially our z is 2i. And obviously the mod of z is simply the square root of 0 squared, because the real part is 0, that's why it's not there. The imaginary part is 2. The mod we get 2. We get square root 2, sorry. And if you want the theta now, simply do a rough sketch. Okay, nice. So 2i is somewhere here, 2i. And we said we are measuring our angle from this side to the side. Guess what? The angle from here to there is pi over 2. So essentially your z, you can write it as square root 2 e to the I pi over 2. And then I can now come and put it inside ln. Square root 2 e to the I pi over 2. And if you follow the steps on the previous page, we'll have ln of square root 2 plus I pi over 2 plus 2a pi. That's how they got to that step. Let me see. Square, square, square. This is not supposed to be square root, because 2 squared, square root is 2. Let's remove the square root here. Yeah. So this is our answer. So you are gonna get a tick here, the given one. And then what is next? Okay, what's next is essentially doing the same thing we were doing previously. So you now look at we'll decide on the number of z values. So because I see they are plotting there, you need to decide on k values, which are gonna ensure that the angle you get here is between pi and minus pi. Then you simply plot the complex number. So I should remove the square. Does that answer the question, or I should do this?
Sorry, can you please explain how we draw the line, the paper line?
How I draw the what?
The paper line.
Or how I draw the paper line?
Yes.
Oh, so that paper line wasn't anything. So I was saying, when we plot the complex number 2i, it is here. And then for me to decide on what theta is, I'm gonna move from 0. I'm gonna move from 0 to that point, but I'm looking at angles. So essentially here, I was at a theta value, which is 0. And then now when I come to this line, the theta value is pi over 2. So the difference between pi over 2 and 0 will give me the angle here, which is pi over 2. Do you follow? Are we still there? It's like I'm alone.
Yeah, we're still here.
Okay, nice. So should I do B? Because we wanted to do calculus also, and we haven't. Where is, I think the person who asked this question was Pupu.
Yeah, it's load shedding. My Wi-Fi was cut off for a second.
Okay, so did you get answered?
Yes, thank you.
Okay, cheers. Let me quickly go to my PC, switch off, go to here. Okay, so if there's no issue with the last question, I'm gonna show you calculus.
For B, because I was doing a past paper yesterday and I just couldn't understand. I have a brief understanding of the methodology behind the solution, but I always get stuck towards the end.
Which question could say?
So it's, yeah, the very last one, B.
Oh, you mean B?
Yeah.
Okay, nice. So B is doable. It is a nice toy. Okay, so let's see what's going on B. So I'm not gonna go through the entire solution. Okay, so B, you were given, zoom out. Let's see. You were given 1 plus I to the power of 1 over 4 plus I. So this doesn't look interesting. It's a complex number to the power of a complex number, and to me it looks scary, but it isn't scary. So let's see how this works. So the first thing you want to do is you do not want to deal with a complex number to the power of another complex number, right? So before we go there, I'm going to quickly remind you of your log laws. So for these kind of questions, they really play a major role. So for your log laws, if I have a to the power of log of a, b, the answer is b. Right, so this is the argument. So if you take your calculator, for example, and say I have, let's say 7,45. So the log of, let's say 8,21, this is a base of 7,45. The answer will be 8,21. So nothing deep. So this is what I want to say before we go here. So which means I can write, about it carefully. I can write, you see the denominator. So what I want to do is to have this as also an exponent. So I'm going to have exponents multiplying one another. So I can write 1 plus e plus I as e to the power of ln 1 plus I. Right. And before you even ask a question, so I'm just gonna say ln x is just log the base ex. Yes. So do you agree that this is the case and it is true, this statement?
Yes.
Okay, nice. So what did we say the previous page? Interestingly enough, we were working the ln of a complex number. And what I said was, let's deal with the ln of that complex number. Let's take that down first and do the dirty work and we'll plug it in again. So I have ln of 1 plus I. So graph sketch, I have positive 1, it's here, I have positive 1, it's here. So it's the first quadrant. And R is just going to be square root 2. Theta here is going to be arctan 1 over 1. Arctan of 1, we know it's pi over 4. Right, which means actually what I have there by the exponent is ln of, now I'm writing it in modulus argument form / Euler form. I have square root 2 e to the I of pi over 4. Then an 8 to pi is more like 8. Do you still follow on until here? So is there anyone who is lost how I got to this step? So this is equal to this here. Are we still following?
Yes.
Okay, nice. So let's go to the next page. Okay, no problem. So essentially, what I have there is e to the ln of square root 2 e to the I pi over 4 plus 2k pi. And guess what? This is raised to the power of 1 over 4 plus I. Are we agree? Because what is here? What is inside here? Also that actually this is simply 1 plus I, but it's written in an interesting way. Right, so this will simply be e to the, if I do what I did last time, it's ln of square 2 plus I pi over 4 plus 2 pi k. This is raised to the power of 1 over 4 plus I. And then all what you do now is from here, you multiply through. You do the multiplying through here. And then you will get a form which is, I think it's presented there in your solution. Okay, maybe I should. Is there anyone who is lost until here? Anyone? So it sounds like it's silent. Like, yeah.
Hello.
Yes.
Oh, Wi-Fi. Can you please explain from that part 1/4 plus I?
1/4 plus I, you mean the step here?
You introduced.
Hmm?
I can't see the screen. I can't see your screen.
Or is it only you who cannot see the screen? Is there anyone else?
Okay, it's fine now. It's fine.
Can now see the screen?
Okay, I ended where we got the expression inside the big brackets.
Mhm. Right, so did you do the multiplying in? You are cutting sticks. Mm. Okay, so are you guys able to see my screen? Because now I'm not sure if my network is failing me or cutting. I'm not sure.
Yes, we're able to see it.
Okay, so I guess the problem is on her side. Okay, so from here, I think you guys should do multiplying in. You do the multiplying in. Let me check the final expression after multiplying in. Okay. So you'll have e to the I. So after multiplying in and doing all the maths, the expression you should have is what was given there. Okay, see how they got the A. I'm going to that I over 4 minus 2 k pi times e to the I pi over 16 plus k pi over 2 plus I can't see the last part. That out I okay, it's supposed to be mm, okay, that's supposed to be happening too. Okay, so nice. This is the expression you are supposed to get as your final expression. And then one thing you should realize is as k increases, this part is a, let me see, as k increases, this part, let's see, so if you make k to be 0, this becomes equal to 0. And then if you increase k, this decreases. If you increase k, this decreases. Change k there. Okay, I see. So here's what you needed to note here. This part, it will always give you something which is more like circular. So this expression you only get after obviously doing the dirty work here. And one thing you should be aware of is for them to get to here, for them to get here, all what they did was to multiply the 1/4 here. And remember there we have inside, we have ln of square root 2, and this is the same as ln to the 1 over 2. When you take that down, it becomes 1 over 2 ln of 2, and then they multiply it by that 1 over 4. That's how they got the 1 over 8. So you do the dirty work of moving from here to here. But now the point is, this part is a circle. So e to the I theta will always give you something which is more like a circle, particular kind of thing. And then what dictates how the circle is going to look is this. Is this one. So if you look carefully at 0, we will have this amplitude of the circle, more like the radius. And then if we increase the k, more like we're decreasing the exponent. So the amplitude decreases. So that's why we'll have something like that with a bigger radius. And then as you increase k, the radius decreases. Decreases, and until. Not sure if that makes sense. Are you still there?
Sorry, can you please kindly explain how we got that spiral shape?
Okay, so so let me come this side. E R I theta, right? Do you agree that e to the I theta gives us a circular, it gives us more, can I say, it gives you a circle, this. When you plot e to the I theta, so let's assume you are changing your theta, you'll get a circle. Okay, that doesn't make sense. Look, so e to the I theta is cos theta plus I sine theta. So if we have r e to the I theta, essentially you have r cos theta plus I r sine theta. Right. And if you remember your complex numbers, this is simply your x. This is simply your y. And if you remember from your polar coordinates, x and y as r cos theta and r sine theta, these will give you a circle with radius r. Right. But now, yeah, obviously your theta should change, increase until. But now the only difference which we have here is we can increase our theta is this. This is our theta. We can increase our theta by changing our k value. Right. Nice and clean. So our theta changes, it gives us a circle. But look at our r. Our r is made up of this. R is the amplitude. Right. So as we increase k, this exponent becomes even more negative. And remember, a to the power of negative something. And when this m is becoming bigger, this is even becoming smaller. It's approaching 0. So as we increase k, we decrease the amplitude. So hence I was saying we started at a certain value, big radius. And then as we increase k, the radius becomes smaller, and the radius is made up of by this part. This is the r if you refer to the next slide, and this is the I theta. So as we increase the K, the amplitude decreases because the exponent becomes even more negative, more negative, more negative. But this is a circle, but now the amplitude is constantly increasing. I don't know how else I can try and explain this. You know, if let's say there was no K here, the amplitude was going to be constant. We're not going to see that spiral vibe. It's just going to be constant amplitude and then you have the circle there. I don't know if this answers the question.
Yes, it does. Thank you.
Okay, so let's quickly move and see this. So what questions gave you a problem in class? So let me see. Did you guys get question 1? So I'm just gonna leave a comment for question 1. So question 1 and question 2, essentially, they are question 1, or there's A and B. So A and B are literally the same. So essentially, when we are given an operator, right? So an operator, let's call it P. This operator is linear if when we are making it to act on Cy, see where there is Y. If we put Cy, the answer we are going to get is the same as us multiplying C and whatever which was originally there. The answer appears like that. Then, okay, condition number 1 has been ticked. So we need 2 conditions for an operator to be a linear operator. And then condition 2 says, if we come there now and say, okay, where there is Y, we are going to put Y1 plus Y2. We should get the same expression as when we are making the operator to act on Y1 separately, and then we add the same operator as when it is acting on Y2. So if we tick these 2 conditions, then whatever which we are dealing with there is a linear operator. Right, so quickly look at what you were given. A. So you were given Y triple dot minus 2Y dash plus Y squared. So we are going to do check number 1. We can do this at the same time. So let's put Cy. We have Cy, the base of Y. And then minus 2 Cy, and then we have Cy, and then we have the square. So where there was Y, we simply put Cy. And then we are like, okay, cool. So I know when I differentiate the constant, I can always take it out. So it's going to be C, and then minus 2C Y dash plus, okay, come here now. When we now come here, I'm going to have C squared, Y squared. And then test number 1 says I should be able to factor out the C and be left with the original expression. Right, so let's factor out the C. If I factor out the C, I'm left with this minus this plus this squared. This is not the original expression because I have this C here, and originally it was not there. So definitely this is not linear. I'm discarding it. Like, okay, cool. The operator here is not linear. No need for me to test for the second one. I'm done. Right, because my P of Cy is not equal to when I factor out the C and then I look at the Y. These are not equal. So the operator is not linear. I'm done with the first one. Easy 2 points. Okay, nice. And then let's look at the second one, which is B. So there's no need for me to carry on and do the second test. The first test failed. So we are done here. Quickly going to B. So for B, let's see what we were given. For B, we're given y double dash minus 2y dash plus t squared y. So let us try the first test. So where there's y, let's put cy. Cy dash dash minus 2 cy dash plus t squared. Put cy, where there's y. And then we know when we derive, we can always take out the c minus 2c y dash plus t squared times c times y. So let's see if we can factor out c. And this will look like the final expression. Factor out the c, we have this. And guess what? This looks like our original expression. Okay, I'm gonna give this one a minute out. So my p of cy, I can see this the same as c multiplying by p of y. Okay, condition number 1 is met. Then I quickly go to condition 2. Condition 2 says, where there is y, go there and put y1 plus y2. And the answer you get should be equal to the same as when you are putting y1 and then you are adding another expression where there's y, there's y2. These are not the same than the expression, then the linear, then the operator is not linear. Sorry. So let's go there and put y1 plus y2. Put our double dash minus 2. Where there's y, let's put y1 plus y2. Put a dash here, plus t squared. Let's put y1 where there's y and y2. Right, let's quickly expand this. I'm gonna get y1 dash plus y double dash, yeah, plus y2 double dash minus 2 times y1 dash minus 2 y2 dash plus t squared y1 plus t squared y2. So if I look carefully here, I have y1 minus 2 y1 dash plus t squared times y1. That part to me appears like all what I did was I went where there was p. I just said, let's put y1. Right. And then quickly, I look at y2 minus 2 y2 plus t squared y2. I look at my expressions, right? Y double dash minus 2y dash minus t squared y dash. So the only difference with this one is there's a 2 here. So which means actually what I did was simply to add y2 dash. And guess what? This is equal to what we initially assumed. So condition number 2 has been ticked. So this is indeed a linear operator. Do you have any question there? Can you still see my screen?
Yes.
Okay, nice. So let's look at question 2 if there's no question for question 1. So question 2, using D operators. I like it when I see D operators. So they are saying using D operators. So we should all know what D operators are. Note, I'm just going to give a brief overview. Find the real valued solution. Okay, nice. Right. So they said the real valued solution. So when solving a differential equation, just a quick comment. Remember, we have two solutions. Solution one is the complementary solution. Complementary solution. They also call it the zero input. So when you see zero input, you write the exam, it shouldn't be something which is out as well. So when they say zero input solution, they mean the same thing. Or sometimes when they're happy, they usually say it is the natural response. Natural response. So if they give you a D operator and say find the natural response, you shouldn't take your head. They say find the zero input response. Shouldn't be surprising. Or if they say find the complementary solution, they mean the same thing. And this is what we usually call our Y0. So our expression which was given was, the second solution, because we need two solutions to solve it. Second solution is called complementary. O is called the particular solution. They sometimes call it the forced response. So when you see forced response, shouldn't be shocked. It's the same thing, and they usually call this Y1. Right, and then the general solution we want is simply a combination of Y0 and Y1. Right, so let's deal with Y0 first. So Y0. So for Y0, we said Y0 is the zero input solution. So we have, let me write this in D operators already. We have D squared minus 4D plus 4. And then I have Y, I have 3e to the minus t. So we are now looking at Y0. And remember, Y0, we said it's the zero input. And the input is this one. The output is this one. So Y0 says it is the zero input. So meaning whatever which is here, we are going to make it to be equal to 0. Because it is the zero input. Our input is whatever which is after the equal sign, the right. So fast forward, what we have is D squared minus 4D plus 4. And we are dealing with Y0, and our input is 0, argued in the previous page. Okay, and then now what we need to do is we need to factorize this. And let's see, two numbers, when I multiply, I get a 4, at them I get negative 4, it must be minus 2 twice. Right, so we should take a step back here and be like, okay, so we have repeated roots. And then if you remember from earlier sessions, I'm just going to remind you quickly. If you have repeated roots, let's say you have d minus alpha to the power of n, your solution to Y0 will simply be, you will have a linear combination of a polynomial, which has a degree which is 1 less than this number here. So what I'm saying is you'll have a plus a1 t plus a2 t squared plus until you have an minus 1 times t to the n minus 1 multiplied by e to the alpha t. So this is what I meant when I was saying we'll have a polynomial which has a degree which is 1 less compared to the number here, which means, fast forward back to our solution, d minus 2 squared Y0. We are going to have a plus bt. I'm gonna stop here because now the order here is 1, and 1 is 1 less than 2. Yeah. Order is 1 is 1 less than 2. Yeah. And then e to the 2t. So that's your easy complementary solution. Done. That's your y0. Okay, cool. So the y1 is the interesting one. So this was easy. Let's go to y1. So y1 is the particular solution. We are no longer making the input to be 0. So we have d squared minus 4d minus plus 4 y1, that's e to the, that's 3e to the minus t. Right. So y1 is simply solving for y1. It's 1 over d squared minus 4d plus 4 times 3e to the minus t. Then from here it should ring automatically that shift rule. I need to use the shift rule. So your brain should shout, should be like, use the shift rule, use it. And how the shift rule works is simple. If you have 1 over, you have y is equal to 1 over p of d. This is whatever your d is, the combination of the d's. If you have this on the other side, at, what the shift rule says is you can move the e to the at to here. All what you need to do is after moving, where there is d, put d plus a. A is whatever which is multiplying the t there. That's the agreement. So the agreement is I'm gonna shift, but where there is d, you should put d plus a. If not, then I'm not gonna move. That's the condition which the e to the at is putting there, right? And then afterwards we can work this. It's easy, right? So fast forward, let's see how this applies to our problem. So y1 is 1 over d squared minus 4d. We don't get
Can I ask,
this.
Kunje, what are the rules that, like, there's something that you need to check before you can use the shift rule? Because, like, sometimes it doesn't work.
I think you need to check if the denominator is not gonna give you 0, isn't it?
Oh, okay.
Yeah. So you need to check if where there is d, put your a and check if this is 0. If it gives you 0, then yeah, it's gonna be a problem. So make sure this is not 0. If it gives you 0, it simply means you will have an integral. It's nothing deep, but we'll see how this works out. See, let's cross the bridge when we get there. Okay, so we have 3 times e to the minus t. Okay, let me use my shift rule now. So the e was like, I don't mind shifting and giving you space. I do not mind giving you space. It is the exams and you are getting child. But the only condition is if the only thing you need to do is where there's d, put d minus me. That's the a speaking. Here it's minus 1 squared minus 4. Where there's d, you put d minus or plus me is then plus my 4. Then we deal with the 3. Yeah, so the e to the minus t was like, I'm gonna allow you to deal with this 3, but only on one condition. And the condition is what we have here. Right. And then fast forward, can see, I can simplify this quickly. Minus t. I think you had d minus 1. That's going to amount to 2d plus 1. I think we had 4 here. Minus 4d. I think we had a negative there. See, I forgot what I did. Plus 4. Plus another 4 here. See if I didn't mess up. Plus 4 minus 4. Okay, nice. And then 3. This is gonna be c1 over d squared 2d minus that 6d. 1 plus 4, and that's a 9 times 3. And then from here, hopefully I didn't make any mistake anywhere. I just pray I did not. I hope I did not. And then from here, all what we are looking for is just a quick recap. If you remember, 1 over 1 minus x. This is the same as 1 plus x plus x squared plus x to the 3 and so on. And 1 over 1 plus x. This is the same as 1 minus x plus x squared minus x cubed minus x to the 4 and so on. So what we want to do is we want to write this as 1 over 1 plus x or as 1 over 1 minus x, so that we can use these two expressions, expression 1 and expression 2. Oh, yes. Okay. So let me copy and move to the next page. Control. So yeah. Let's go. Paste here. Yes. Nice. So I'm looking for a 1 plus there on the denominator. So I can factor out a 9. So I can have e to the minus t. If I factor out a 9 there, what I'm going to have is I'm going to have a 1 plus I'm going to have d squared minus 6d over 9. Then this is acting on the 3. Then this works. I can now use my equation 2. Right. So equation 2 quickly was saying if I have 1 plus x, I can have 1 minus x plus x squared minus x cubed and so on. So quickly I have e to the minus t over 9. Now I'm gonna have 1 minus the x in our case is d squared minus 6d over 9. And then I'm gonna add again squared minus 6d over 9 and so on. This is all acting on 3. So now I'm just gonna introduce 3 in here. So obviously here 3 is gonna be square here. Square here. If I introduce 3 inside this bracket, it's just gonna be a 0. If I also introduce 3 here, derive a constant, it's 0, derive it twice, it's 0. So the 3 is only gonna come here. And when it gets there, it becomes 3. And then essentially what we have is simply 3e to the minus t over 9. And the answer is simply e to the minus t over 3. And this is our y1. And our y total solution is y0 plus y1. Y0, if I remember, it was a plus t to the e to the 2t plus, and here what we are getting is what we are getting is e to the minus t over 3. Any questions? Any question?
Sorry, may you please repeat the condition for the shift rule?
Okay, so for the shift rule, I said when you put in the alpha, you should not get 0.
Okay, thank you.
Okay, so fast forward. What is the next question? Okay, let's see. Oh, so the next question is much the same as this one. Nice. So let's see, question. This is question 3. This is where yes. Okay, nice. So let's go back to this font. Let's see what's going on here. So for this one, we are given b squared plus 1 acting on y. I think it's 4t cos t. Let me quickly check. Okay, yeah. This is all nice. So we need to figure out, obviously, as argued before, we said our solution is made up of y0 plus y1. Right, so for y0, we'll make the input to be 0. So let's deal with y0. So y0 is d squared plus 1. Y0 in the input is 0. Y0, we said it's the 0 input complementary function or slash the natural response. So if I try to factorize this expression here, I will get d plus I and d minus I. 0. And just a quick reminder, I think it's a reminder. So let's say z is, so you will need to note this down. Let's say z is a plus ib, it's a complex number. In this case, yeah, is a complex number. If you have d minus z and d minus z bar, so I hope you can see that this and these are conjugate. Essentially, we have something like this. If you have this, then the solution will always be e to the real part of z times t multiplied by p cos of the imaginary part of z times t, close bracket, plus q times sine of the imaginary part of z times t, close and close the bracket. Right? So if you look carefully, the real part of z, the real part of z is simply a, and the imaginary part of z, whatever is multiplying the I, is simply b. So which means the solution for this z value here, by now we have something like this, is simply e to the bt, open bracket p, cos of the imaginary part of z is a, mistake. Real part is a, nice. Then here we are going to have bt plus q sine of bt, right? So I'm saying this to say I need to figure out here from this bracket, what is my z? And then if I know my z and I can write it in this form, then I can simply shoot straight to the solution here. And I'm going to get my marks. Okay, so let's see. So I have z minus I. No, it's d. D minus I. So I have d minus I and d minus I. That's the plus 10. Right. So I can see from here that, oh, actually, my z is I, and this is z bar, and it's the conjugate, it's negative. Same way here, I have the z, and here I have the conjugate. So that means my z actually is I, which is just the same as 0 plus I times 1, which is the same as saying the real part of z is 0. The imaginary part of z is 1. So I can come straight to my solution here and say, okay, look at this one. So we should have e to the power of the real part of z. I'm looking at this term. The real part of z for our case, it is 0. So I have e to the 0 t p cos of, I have the imaginary part of z times t. The imaginary part is 1. So 1 times t is t plus q sine of, I have the imaginary part of z times t. The imaginary part of z is 1. So 1 times t is t. So e to the 0 is simply 1. So your final answer was p cos t plus q sine t. That's your easy y0. Complex exponentials is the thing. Are we still together?
No, sir.
Where did I lose you? I think.
Sorry?
I think you are cutting.
Can you hear me now?
Yes.
Can you please start from where you wrote with the green pencil and then going downwards?
Okay. Let's give it a try. Let me write that part. Okay. So we said, let's say we have a complex number. Z is A plus IB. And you do your D operator things. You factorize, and then you end up getting a form which is like this. And when you look here, you're like, okay, this complex number is the same as this one. But the only difference is one is the conjugate of the other. Right. So immediately when you realize this, I said you will look at what your Z is and then write your Z in this form. And then your solution to this will be e to the real part of Z times t multiplied by p cos the imaginary part of Z times t plus q sine of the imaginary part of z times t. And this is nothing complicated. The imaginary part of z is whatever which is multiplied by the I, that's b. The real part of z is whatever which is standing alone, which is a. So which means if I quickly translate the solution, it becomes y0 becomes e to the real part, we said it's a. So I have at p times cos of the imaginary part, I have b times t plus q sine of the imaginary part, I have b times t. This is the solution to something which looks like this. And then fast forward to your problem. When we factorized, we got something like this, d plus I, y0. And then I was like, look, this we can write it to look even much more nicer. D minus I times d minus I, y0 is 0. And guess what? This now looks more like this, because I know my z is I, and this is the conjugate. The conjugate of I is negative I. So I can say that actually my z is simply I, which is just the same as the real part is 0, I times 1. So from here, I can see that my real part of z is 0, and my imaginary part of z is 1, whatever which is multiplying I. Then I'm going to use the standard solution and say, okay, cool. So I'm just going to plug in. So the solution is E. The E is this one. This one. The solution is e to the power of the real part. And the real part of our solution, we got 0. So that's 0t. P cos of, we should have the imaginary part of z. The imaginary part, we got 1. So that's 1 times t, which is t. Plus q sine of the imaginary part of z times t. That's 1 times t, which is t. And we know this is just going to be a 1. So our solution is p cos t plus q sine t. Does this answer the question?
Yes, thank you so much.
Cheers. And then for y1, essentially you do the same thing we did with saying, okay, use the shift rule. But the only difference is, so y1 will be 1 over d squared plus 1. T squared plus 1. And then 4t cos t. So we cannot work with cos. So all what we know is the most complex thing, which we know is we know how to use the shift rule when there's e to the alpha t. So cos t looks really weird, but we know that actually cos t, or e to the alpha, e to the I t, is the same as cos t plus I sine t. So if you can look carefully, the real part of e to the it is simply cos t. So meaning wherever we see cos t, we can replace it by putting the real part of e to the it. Right. Fast forward. That means all what we can do, we can say 1 over d squared plus 1 over 4t. That cos we can replace it by re e to the it. And since this is just a real thing, and this is real, we can put the re outside. like this and deal with everything inside. Times 4t e to the I t. And then from here you apply the same rule you used. So same thing I proposed. Let me see. Same thing I proposed here. Apply this, and your f of t is simply 4t for that equation. So you simply apply what we did here. You move the e to the it, and then you deal with this accordingly. So let me quickly run through. I'm not gonna do the entire thing. So that's the real part of. So e to the it says I can move this side only if when I move where there's d, you put d plus I plus 1 times 4t. Yes. And then we'll quickly expand that side, e to the it, 1 over the denominator is going to be d squared plus 2di, plus I times I is -1 plus 1 times 4t. And to the next page, what I end up getting is e to the it, 1 over d squared minus 2id times 4t. Nice. So now I'm looking for the form. I'm looking for one of these forms. Remember, it's previously argued, looking for 1 over 1 plus x, which is going to be 1 minus x plus x squared minus x cubed and so on. Or I'm going to be happy if I can get 1 minus x is, this is going to be equal to this. So I'm looking for one of the.
Sorry, isn't it d squared plus 2id there?
2id. Okay, let me see if I sign. Yes, thanks. This was going to be a killer, but at least for a sit-down exam, you'll probably lose 1 point for making that sign mistake. For an online exam, they do die. So let's see. I'm looking for either form 1 or form 2. And the only way I see I can achieve this form is if I divide by, let's see, 2id. If I remove 2id, the denominator, where there was 2id, I'm going to have a 1. Right, and the rest is history. So let's see. RE, e to the it. So I'm saying let me remove 2id. If I do so, I'm going to have a 1 here, plus I'm going to have d squared divided by 2id. And this is acting on 4t. And then let's try and make this to look a bit neat. Okay. No, I don't want to go to the next page. So I have e to the it over 2id, 1 over 1 plus, I think I'm going to have d over 2i. This is acting on 4t. Yes. So let me take this to the next page. Copy. Okay, so how did I lose my background? How? Okay, problem. Let's paste here. Paste here. Okay. So now I can do my usual expansion. E to the I t over 2id. I have the form of 1 plus, so I'm going to have 1 minus d over 2i plus d over 2i whole squared, and so on. This is acting on 4t. 4t here. It's supposed to be another bracket. And let's see. Re e to the it over 2di. If I introduce the 4t inside here, here I'm going to derive it twice. It will be 0, so the term is out. I put it here. I'm going to derive 4t, and I'm going to get a 4 and then divide by 2i. I think that's going to be, okay, let's take a 4t here first. I'm going to have 4t minus, when I take it to this term, it's going to be 4 divided by 2i, and that's going to be 2 over I. Okay, nice. And then what this 1 over d does, what this d in the denominator means, 1 over d is simply integration. So meaning whatever we have here, we need to integrate. Okay. So I'm going to have the real part of e to the it over 2i. Then I'm integrating this 4t minus 2i minus 2 over I t. And then fast forward, it's the real part of e to the it over 2i. What I get after integrating here, integrate 4t, that's going to be 4t squared divided by 2, it's 2t squared. And then I'm going to have this, then plus c here. And then we now need to look for the real part of this thing. So funny enough, I'm going to need to deal with the e to the it. Take it to the next page. This was a long one, but it's long because I'm trying to. Okay. Okay, so let's deal with e to the I theta. We know this is cos theta plus I sine theta. So I'm going to have the real part of cos t plus I sine t over 2i multiplied by 2t squared minus 2 over I t plus c. Okay, cool. So let's multiply through what is inside there. So I have 2t squared cos t over 2i plus c cos t. I'm going to have 2. Okay, I'm going to have a plus. The plus is going to come from this I multiplied by this I. I times I is negative 1. But there's a negative here. So I'm going to have plus 2t cos t over the 2. And then plus multiply this and this. That's c cos t over 2i. Then let's deal now when we multiply in the sign. So that's going to be plus. Oh, the i's are going to cancel with the sign. I and the I are going to cancel. Nice. So essentially what I have is 2t squared sine t over 2 plus I have 2, I have minus 2t over 2I, and then sine t. And then lastly, what I have c sine t over 2. And then all what I'm gonna look for is inside. I'm saying the real part. So I'm gonna ignore everything which is related to the I. So this has an I. This also has I. This also has I. Okay, nice. So let's see what else has an I. Yeah. So I think what doesn't have the I here is simply t cos t is t cos t, because the 2's will cancel, plus the 2 and the 2 will cancel, t squared sine t plus this and this, it's c divided by 2. I can make it an arbitrary constant, call it k sine t. Right. And then this is my y1. So finally my y total, which is y1 plus y2, it is gonna be t cos t plus q sine t plus t cos t plus t squared sine t plus k sine t. And then this is our final answer. So the q sine t and the k sine t will combine and give them a new value. But that's what they expected us to do here. I hope I didn't make any mistake. Anyway, yes. Are we still together? So let me write this in compact form. Still here. Can you still see my screen?
Yes.
Yes.
Okay, nice. Good. The silence is scaring. Okay, nice. Okay, so let me quickly do some stuff. So our final answer will be t squared sine t plus t cos t plus let's say let's combine this and this and name them c sine t, and we have another cos here. That's going to be p cos t. So yeah, I think this is what we're supposed to have. Yes. So we are done for this problem. We are done. And then what's going on below? Question 4, it was 5 points. Okay, so let me quickly run over question 4. I doubt I'm going to do the entire question 4. Let's see. Question 4. Consider the operator where c, k, 0 determine for all values c okay, so let me quickly just note what they said. So they said k is positive. some positive number. Nice. Yeah. Obviously, this implies k squared is also positive. Okay, easy. And determine all values of C for which P of D is stable. Okay, so for stability of D operators, I need to comment on that because it's not like you get the same question. Stability of D operators, or so let's say after factoring your D operator, you have D minus alpha, D minus beta, and D minus, say, gamma. Yeah. So let's say after factoring out your D operator, say this was D cubed as whatever combination, you get these. And then these, your D operator, we call it P of D, is gonna be stable if and only if all these, I'm gonna call these poles, if all the poles, they are on the left hand side of our plane. Okay. What this means is you will draw your real imaginary plane. Real, this is the real, this is the imaginary side. You will plot these. So let's say these were numbers, something like D minus 2, minus 3, D minus 4. You will now solve for D. D will be 2, D will be 3, and D will be 4. And if you plot these, 2 is here, 3 is here, and 4 is here. And guess what? These are on the right hand side. And the system is unstable. So fast forward, for a stable system or stable D operator, every pole should be on the left. Immediately when we have one of them on the right, if you solve here, maybe let's say alpha is -7, is somewhere here, beta is somewhere here, but gamma decides to be on the right. Therefore, that D operator is no longer stable. All of your solutions should be on the left for stability. One of them is on the right. When you solve, then that entire D operator or system is unstable. So people who do what TSF, I'm sure they should know this by now. If you don't know, it's okay. Right, so I was saying this to say, but let me look at my question. I had to say this before doing the question. Go ahead. Fast forward is, and then the next thing they said is, so we know that they are saying we should force this to be stable. I mean, all our poles should be on. So it can be anywhere here, as long as they are not this side. And then they are saying underdamped. So what does underdamped mean? Did you get my question? Still here. Silence is worrying.
Yes.
Yep. So is the silence because people do not know or what?
So isn't it when the value the exponent of e has to be positive, then it will be overdamped or underdamped, something like that. I'm not sure.
Can you please repeat?
I'm not too sure about what I'm about to say, but I think it has to do with the positivity of the exponent of e. If it's positive, then it's underdamped. I'm not sure though.
Okay, so yeah, still thinking. Anyone who can give it can shoot. You have something.
Isn't an underdamped system one which oscillates towards zero?
And then what about an overdamped?
To infinity.
And then critically overdamped. Critically damped, not overdamped.
Equals to zero.
Okay, fast forward. Oh, this is so interesting. So fast forward, you guys are right. So under them, the system should oscillate to zero. So it's something like this. Um, Back in the days, we're doing sine and cosine graphs. They look something like this. And then an underdamped system will, it's in an exponential order. It will do something like this. And then if it takes the sine and the cos with itself, it's gonna do something like this to the wave. To do something like this, and then eventually it will lie to zero, something like this. And for you to have this kind of system, think about it. Think carefully. Look at the blue line and look at the red one. Your answer, your solution should be something like this. Can be a combination of cos and sine. T plus q sine of b t here. It should be something like this, where a is greater than 0. Do we all agree that this? You don't need to agree. So I am proposing that this expression will give us something which looks like the combination of the blue graph and the red one. So what's your take on?
So I couldn't hear you properly. May you please repeat the last portion that you mentioned?
Right, so I'm saying my proposal is the y I wrote here is gonna give me the combination of the blue graph and the red graph. So that's my proposal, and I need your comment. For your take. Silence. Silence. I'm waiting because I can do the talking. It's like So what do you guys say? Okay, so let me do the solution. So just think, I'm gonna need you to think about this carefully. So it's more like an exercise. Just think about what I'm gonna write or the next page. So you guys told me that underdamped is when we have something which isn't, when it is decaying exponential. Right. Okay, this works nice. So we can have two forms where we have something decaying exponential. It can be like this, or it can be like this. And I have this. And so on. So let's think about this. So let's say after solving, say you solve your thing, d minus, say you have minus alpha, and then you get, and let's say you have d minus beta, and you have this. So your answer here is gonna be a e to the alpha t plus b e to the beta t. So this will not make the point I want. It's true, but this solution is more like what this graph represents, right? And then this graph here, combined with the blue, is represented by a solution which looks like e to the alpha t multiplied by p cos of t plus q sine of t. Maybe here there can be even a constant. And this only comes, this solution we know, complex exponential, it only comes if we had minus, if we had a factor which was a complex number, then equal to something. If we had a factor which is a complex number, this is going to be the resulting expression, right? And then fast forward, we have, let me write that expression and you will see why. See what I was saying. D. We have d squared plus cd plus k squared. So I can achieve an expression which resembles something which is decaying exponentially by remember our determinant, because literally all what we are doing here is we are solving for the poles to some extent. Yeah, let's say so. Think about that. So when I solve for my poles, determinant, remember it's b squared minus 4ac. I can have the poles as real poles, meaning there's nothing complex, and I can still achieve something which looks like this. Or alternatively, the discriminant, if it is negative, then it means we are going to have the square root of something which is negative, because discriminant is simply squared minus 4c. We are now saying this is less than 0, then clearly we are going to have a complex number, which means our factors are going to be complex, and guess what? We'll have this form. And still we can achieve some paying vibes using that form. So hence we are going to test this and this. So am I losing anyone? Am I losing anyone? So we need to do some testing here. And there is silence. Okay. I think I'm still here. Okay, so because you guys are not interacting, I don't think, and then it's gonna be for you to go and look at that solution and make sense. Right. Yeah. I think so, because many of you cannot say a thing now because you are tired. So I think we can call it a day, and I hope we answered all the questions.
So,
Yes.
so these are the solutions
What do you mean?
for question 4.
Oh, you are saying what?
Now I'm asking.
Oh, no. Are you asking if this is the solution?
Or it's a method on how we're supposed to go about when solving for question 4.
Yes. So I was showing you why first they had to consider this and this. And you guys are so silent, and I'm like, I might as well leave you guys to go and get the memo, because I'm like, am I losing anyone in one side? So yeah. So I was just explaining why you would want to consider this a, and then from here, so let's see, b squared, c squared. So our determinant, I'm not gonna finish this solution. B determinant is c squared minus 4. Our a is 1. Our c is k squared. So we have c squared minus k squared. But remember, where is my 4? 4 here, 4k squared. So let me write this as c squared minus 2k whole squared. But remember something here. The only thing we want to monitor is c. So c is the variable. C is our variable. So let's look at the case where we are saying the determinant should be greater than 0. So if you remember from high school, this will look like when you solve. You'll have 2k here, you'll have minus 2k here.
Sorry.
Yes.
Okay, how does C become the variable?
Okay, so k was given to be greater than 0, right? And what we are trying to do, let me read the question where C, determine for all values of C. So meaning we can assume K is a constant. Whatever constant, we don't know what it is. It can be 1,000, it can be whatever. But K is a constant. C is what we are concerned about. I don't know how, I don't know if this makes sense. So K is not known, but we will treat C as the variable here, something which we are interested in. It's like, consider this expression. It's like it's like x squared minus 4 is greater than 0. If I go to my graph, I'm gonna plot a 2 here, a 2 here. And then the graph, I think it's gonna be it's gonna be like this. Then greater than, I'm focusing on this region because I'm looking for more focused on the X values. So in our problem, we're like, okay, so A is not known, but focus on the C. Show if that makes sense. So K, you can treat it as something which is not constant, it is constant, but just that we don't know the constant. So I'm using the same logic as here, but I'm applying it here. Not sure if that makes sense.
Yes, it does. Thank you.
Okay, cheers. So quickly, this is our rough sketch. And we all know from school, exclude you. And then we are going to shade this region. It's this one. So essentially, that region is saying our C must be greater than 2K. This is the side. Or the other side is saying our C must be less than minus 2K. Okay, cool. So let's keep these down here. And let's move to the other one, which is greater than. Or which is less than. So the other one, it is like this. So essentially we have C squared minus 2K all squared less than 0. Fast forward, I have 2K here, it's 2K here. I know my graph. This, I still use graphs, so you can use whatever works for you. Maybe tables do. And less than 0, this is the region which is below 0. And this region is the region where C is between 2K and minus, let's see, it's the region where C is between 2K and minus 2K. So how do we go about concluding from here? So it's a question to you. Let me write that expression. It was D squared plus C D plus K squared. Yeah. P of D. How do we go about concluding here? Let's think. Let us think. So remember one thing I said. I don't know if this graph makes sense. This one. Let's go and look at our solution. So we have D squared minus plus CD plus K squared. So if we solve for the D here, our D is going to be negative B to C over 2 plus or minus the square root of C squared minus 4K K squared over 2. Right, and we have two conditions. We have the one where we are saying C can be between 2K and minus 2K, it shouldn't be included. And we have the one where we are saying C must be greater than 2K. Or C can be less than minus 2K. So we need to decide on what C should be. What do you guys say? And remember something, on the left, remember we said for something to be stable, it should be on the left-hand side of the plane. Remember, on the left-hand side, if you have a complex number, Z is A plus IB. The real part, that complex number, the solution must be less than 0, must be negative. So do you guys see from here that actually my negative C over 2 is going to be part of the solution. It's going to form the real part, assuming we make this to be complex. Right, so this is the solution where let me check. This is the solution where the determinant is less than 0. This is the solution where determinant is greater than 0. Nice. So look at this carefully. If we take this solution, the determinant is less than 0. Meaning here we are just going to come out with some I times some number. Let's focus on this part, negative C over B. If you want this to be stable, then this thing must be negative. So which means for this to be negative, my C must be positive. I don't know if that makes sense.
Please repeat the last part.
Right. So look at my solution. Let me move this. So I am saying let's consider the solution where the determinant is less than 0. And that's the solution. Right. So I'm saying if we're saying the determinant is less than 0, what is going to come out of this square root is simply going to be I times some value. Nice. Right. And I said on the second part, on the left side of the real imaginary plane, the real part must be less than 0 because we have negative x's here. Makes sense. And when we look at our square root, our solution, this is going to form the real part, our solution, the negative C over 2. And the negative C over 2 must be negative. This to be stable, must be on the left. So I'm arguing that because already there's a negative here, the C must be positive. Does it make sense?
Yes, it does. Thank you.
Yes, so it does.
Nice. So the C must be positive. Right. Okay, nice. So now the question is what? So for us to maintain this, so when we choose our C, we should be careful. Look at the square root now. This is so interesting. So our C, we have figured out it must be positive. But now the question is, what limit is there on the upper side? So look at the square root. We have C squared minus 4. Let me just put the 2k squared. That's the minus 4k squared. Our C, we can make it to be positive until it reaches this value. Because if we make it very, very big, under that square root, you will end up having a square root of a big number. And then if we are using the positive sign, we'll get negative 2 plus 2 over a big number. I shouldn't be calling it. Let me call it a big number, B, and then we'll end up having a big number over 2. And that's going to be a positive x value. It's going to be this side. So which means as much as we want C to be positive, we need to restrict the C. And how we restrict the C is it should be positive, but it shouldn't exceed a value of 2k. Because under the square root, we have C squared minus 2k squared. So the c can be very big, but it shouldn't be bigger than 2k. Because if we make it to be bigger than 2k, it's gonna give us an issue. Let me see if I can make an example for you. Let's take c to be equal to 9k, right? We go back to our solution. So this was, there's no easy way out. So if we go back to the square root, we're gonna have c squared, which is 81, k squared minus 4k squared. And what you get here is 81 minus 4, no, that's 77. Yeah, so 77 squared, in the square root, so it's square root of 77 times k. And remember, k is a positive number. And then what we essentially have is negative c plus, when you take the plus solution, plus 77 k over 2. This can give us a problem depending on the value of k. So that's why we will limit c based on k. So this is our upper limit of c. So essentially our c should be an element from, should I include 0? Let me see, 0, 0, 0, stable, until 2 for that solution. Are we still together?
Yes, sir.
And then literally we are done. We are done. So we need to go back. Wait, I want to go. I want to come. Yeah, it's to be complex. Okay, I forgot what I wanted to say. So I'm gonna wait for a question. Then probably I'm gonna know what I wanted to say. But that's essentially the thing which the lecturer was saying in those steps before. But you would need to reason down this thing. That's the thing. You see what I was saying. Instead of saying it, if I was in an exam room, I was gonna instead write it down. See, just like what I see here. It's okay. I know for stability, my poles should be on the left. And looking at this solution, the real part is gonna come out from negative c over 2. And if this needs to be on the left, then clearly my c should be a value which is 0 or greater than 0. And then I'm like, okay, cool. So how big can I make c to be? I make c to be very big. This number will eventually be a very big number. It will add with a negative number, it will give me a positive big number, which is this side. So I don't want such. So I'm gonna need to restrict my c value. And then I think carefully about how the c relates to this. And then I restrict the c, and then finally I come here. Right, so just think about it. You will get it right. So if there's no further question, I think I'm gonna call it today. And then the people who are doing TSF, I don't know what pen we can make. See. So I'm gonna pause for a few minutes and wait for questions. And then if there's no question, we can all go and sleep. If you have any question?
Sorry, may you please go over how we can restrict our C based on K? on the previous question.
Okay, can you please, I think I can write something down for you after the meeting. It's like I need to rush somewhere. Yeah,
Okay, thank you.
yes. And then do we have any other boiling thingy? Now I cannot answer a question. Let me see this and see what's up here. And